Professor, I think, Rodrigo Bissacot, and the title is phase transitions which are invisible for the pressure function. So yes, it is. It's something about async model, so it will be about mathematical physics. So there is a close connection between different groups in our excellence center. So Rodrigo, please start.
Okay, thank you for the invitation to give this talk. It's a problem. There's a delay here. Okay, maybe it's good now.
Okay, please. I just want to say that because of some PhD defense, I will have to escape before 11. So in such case, Darek Chruściński will chair our today's seminar in the part of questions. So
okay.
So that's it. Please continue. Please continue.
I prepare something that I will focus more or less in the physics part. Let's say in this first part, and after just maybe some remarks about the unidimensional systems, and at the end, maybe just I put on the slides. I guess in the slides for those that they are interesting. That I maybe probably just mention the connection with the ergo theory and thermodynamic formalism. Well, my background is I started in the pure mathematics, and after I jumped to ergo theory, and motivated by ergo theory, I jumped to mathematical physics. This more or less is my background, and this talk will be exactly about the, let's say, the main model of statistical mechanics, which are the Ising model. After you have generalizations to long-range systems, but I will, let's say, focus in this class of models first, short range, and after long-range models. And essentially, this is kind of fun history, actually, because in Brazil, we don't have a strong school of mathematical physics. And this is a kind of very lucky person when you, let's say, you find something in the literature about an old model. This model has 100 years, and which was precisely this class of model when you consider the K fields. I will explain the model, and you can stop me to ask about the model if you want. So this will be the main focus of the talk, and the let's say the main result, the main recent result is about long range multidimensional models. This is, I will put the reference in the slides, but everything is my homepage. So the let's say the configuration space essentially will be the -1 + 1 power to ZD, means that in each side of your ZD you have to choose between plus or minus. This in the entire ZD. You take this metric. It could be another one, but this is sometimes easier for the calculations. You have the boundaries of the sets. If you have a set on ZD, you have the first neighbors. Let's say this. And well, this will be my configuration space, at least for the, okay, then the most part of the talk will be this. And okay, this came from physics because you have the particles and you have the spin there. So this -1 + 1 represent the spin of the particles. This kind of model they call spin systems. And after you have the configuration, you have to say what is the energy function of your model. So which means that differently from ergo theory, in general in physics you want to calculate things. So in general it's very common you start with let's say finite objects, and after choose some kind of procedure and take the limit to the what in general they call thermodynamic limit. So what is happening here that you have a box which is lambda, and here you have the let's say inside you call sigma, and this each of let's say is plus or -1, you interact for everybody. Of course, to range that is not explode, you have to put some decay in the constant couplings. So for us, I will more or less soon tell you what is but you can more or less nothing will be different from this. For example, this alpha is bigger than D in the case of long range, or when the short range will be 0 if you are far, or will be just positive number if you are close. So this part of the Hamiltonian tells you the interaction between the spins. So you have a spin in this point, you interact with everybody with some intensity that is here, and you have some kind of external force called external field, which is this parameter here, the family of real numbers.
Rodrigo, sorry, is sigma a configuration on the space?
Sigma is a configuration.
Okay.
Yes,
okay.
yes. Sigma exactly is. Very sorry, Christoph. And for each of these points, you have plus or -1. Exactly this. This is sigma. So, but what happens here is that, of course, you have infinitely many, but the way that you construct this measure is the following: you fix a finite box, and this is random part, let's say, and outside there is something fixed that we call boundary condition. So this is the usual way to construct. So here outside you have some fixed. This is fixed, and here is your random variable, let's say, and here is the lambda. And for each finite lambda, here you let free these variables, and here you fix it a priori some boundary condition. In general, is plus, everybody is plus, or everybody is minus. This is the usual one. And you construct this function. This function is well defined because, okay, if you put the right weights here, this will be a finite number, and so on. So this is the interaction between the spins, and this is some kind of external force. Let's just a kind of a spoiler. This external field is really because you can prove that if you take the limit, for example, after if you take the limit when h is plus infinity in your measure, I will construct a measure in a moment. So let's say some point. So this probability of C plus 1, for example, will be 1. So you see, if you have a very, very high field in some position, this force you will give extremely large probability to see the plus 1 there. So it's really a force. You see, you're pushing the spin according to the sign of the field. So in general, okay, the first model, of course, there is no field. It's just I'm more or less bad choice, maybe because this is the main Hamiltonian of the talk, but maybe a good choice is running a bit to get intuition, and after you see the more complicated. But this is the more general thing that we can see here. The couplings should be positive, and we say it's ferromagnetic because well, this gives to you some intuition that you are more or less favorizing the spin has the same sign, but also you have some inequalities, which exactly allows you to get these thermodynamic limits. If I change the sign here, the theory is very incomplete. So you have the field that I already told you, and you construct the final volume Gibbs measure, which is actually have these weights. And this is an atomic measure, which is concentrated on this on the configurations where you have here's a lambda. Outside you have omega. So if a configuration does not agree with omega outside of lambda, you put 0, just this. And if outside of lambda you see omega, so you put this weight. So this is a well-defined measure. It's atomic measure, of course. You have just a finite numbers of configurations, and you have this weight. And this is just a normalization factor to be a probability. And this we call finite volume Gibbs measure with boundary condition omega. Okay. So this, of course, as you see, is a total general procedure. I just pick up a model. If you have another Hamiltonian, we just use the same receipt. Okay. And now, well, this is when someone tell you about the easy model, they is telling you about this. So you have just first neighbor interactions. So you have a spin here. You just interaction with the first neighbors with intensity J. And this is what we call long range easy model, which is okay. Your interaction is weaker and weaker when you are far. You have to assume this, otherwise it gives you infinity. And okay, this is exactly the main model, the most famous model of the theory. So okay, so okay, basically most of the talk will be about these two class of models. So here I have some parameter which is more or less free because I can get a bigger and bigger alpha. But when I have some kind of class of model because I didn't say which is exactly the alpha, but just alpha bigger than D. Okay, and now about Mario's question, if we don't use Gibbs as a neighbor for these measures, yes, but the problem is that after a while, a lot of measures start to be called as Gibbs. This that I just mentioned to you, in general, the physicists they call Gibbs measures, finite Gibbs measures. But a lot of other measures people start to call Gibbs. So at some moment it was some kind of confusion in the literature. And now more or less people know when they are equal, when they are not. There is some gaps yet, but in general, if people stop to use Gibbs or otherwise put Gibbs-Bowen or the DLR equations that I will mention here, precisely because of this. So if you are in the probability, let's say in physical mechanics side, or also probability people that work with Gibbs measures, if they call Gibbs, probably they are discussing about these measures, which are the accumulation points when you take weak limits of these finite volume Gibbs measures. So since the space is compact, you take the bottle of sigma, blah, 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 and you have accumulation point for sure. And you take all the accumulation points when you run of all boundary conditions. And after this, you take the closest convex hull, which means that the close of the convex combinations of all these limits, and this will be the set of Gibbs measures. So of course, this is some kind of abstract set, but what happens in the reality that you have some kind of special boundary condition, which is when you choose boundary condition which everybody is plus, or boundary condition with everybody is minus. So which one the most important one? And but to be honest, this is the characterization to go fast to existence of Gibbs measures. So just accumulation points, of course, it exists, and okay, you get for free. But to do the proofs is not like that. So in general, people don't work really. When you have to prove things, you don't use this characterization. You use what we call Dillard equations. Okay, you can state another way, but this is a good option also. So, okay, D is from Dobrushin, L Dobrushin is L from Ruel, and L of Lanford. Okay, what this equation says to you? That is, you have to let's say you have a probability with a probability, and you impose the following: when you take a lambda, you can consider the sigma algebra of the outside of this lambda. So we call this. So the events which depends only on the coordinates outside of the box. So you fix this sub sigma algebra. So, and you say that you impose to this measure the following, which the condition expectation of the measure, let's say put an event here, respect to this sub sigma algebra. Okay, now you see this is an event. You can put a characteristic function if you want, if you like. So, but you take the condition expectation. So this is a function. Okay, so apply this function in some kind of configuration. Okay, I do. So you impose that these condition expectations coincides, gives to you, precisely the Gibbs measure of finite volume that I just defined before. So you know what is a finite volume Gibbs measure. You have this, and let's say you want to say that an infinite volume measure is a Gibbs measure for this Hamiltonian. Let's say that you construct with this this finite volume. So you have a Hamiltonian, and you have a probability measure. So you impose that the condition expectation of C something outside for any event evaluated to any configuration coincide with the finite volume Gibbs measure. So this there is okay. There are another characterization that, but this is a good way to think. You will find something close to this in paper of Dobrushin, and Ruel and Lanford, they wrote another one which is used. They are using C-star algebra. Maybe it's not clear for you when you read the paper, but actually they are is the same thing. So, and maybe it's not obvious now, but it's an exercise actually. Okay, you have to use a little bit of functional analysis, but you can prove that these two definitions coincide. You see, it's not obvious that you have a measure which satisfies this. You see, you start with some Hamiltonian, you construct this. How you don't know if you have some measure which coincide with which this condition expectations coincide with this. So that's why it's easier to talk about this definition, but you can prove that they are the same. Okay, so for me, Gibbs from now is this definition, one or another one is the same thing. And I'm testing in the Ising model or Is-type models, let's say. Now for my colleagues from here of my corridor, Christoph, Marius, everybody. Well, in this talk that we have in our seminar in the last weeks, we discussed a lot of about the eigenmeasures for the while operator, and okay, there are proofs before them, but this is a nice reference because the proof is simple and works for any continuous potentials. So if you have interaction, you construct a potential, and you can prove the eigenmeasures of the whole operator. Actually, they coincide with the DLR measure, which I just defined. And of course, okay, what is a box here? You just take the box, starting with the blah, 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 and here. So you have the outside of the box, you see? So take this sigma algebra and take the condition expectations and so on. So you can prove that DLR measures coincide with the game measures. Okay, there are previous proofs, but they have an independent proven for just continuous potential. For example, for regular potentials, more than continuous, I think is much older than this. But this is a nice and simple reference. We can get the proof. Okay, just to connect to ergo theory. And phase transition. Well, you know, if you work in interface of two areas, this always happens. People use the name for different things. And what phase transition could be a lot of things, and a lot of different senses. But for example, if you get let's say a Bible of Gibbs measure with the Georg's book, which is kind of the main reference for the theory, is very abstract and very very general book about Gibbs measures, and the definition there is precisely this: that you have a phase transition. If for some, this beta means for us means the inverse of the temperature. You have more than one Gibbs measure. This is for actually for any Hamilton and so on. And okay, in dynamical systems, it's very usual you define a phase transition as the point when the pressure is not analytic. So these notions coincide sometimes and sometimes not, and this is more or less the main goal of the talk, is present a phase transition which is not connected with the lack of analyticity of the pressure. This is even let's say the most famous model. If you do some kind of the right modification, the pressure does not tell you anymore about the phase transition or not. Sometimes the point where the pressure is not analytic, exactly the point where the set of Gibbs measures change, sometimes not. Here in this talk we have both examples. But one important thing maybe is to highlight that this is a extremely general theorem, which says to you there's the following. Here you have the beta. Beta for us is always the inverse of temperature. If you have a model, you can, okay, if you hate physics, you just put some real parameter in front, but this result, of course, came from the intuition from the physics models, the physical models. So what happens that basically for any model, for any interaction, for anything, it's totally general. There is no model is a term for when the beta is small enough, which means high temperature. This is another thing that happens here. we have a lot of results which depends of the temperature is high or not. What happens at the end to close the gap, the entire region is extremely difficult. In general, you don't know this. For a couple of models, you know, the rest you don't know. And people believe you, maybe you never will know. And what happens that this Dobruch uniqueness theorem tells you that if you are in high temperature, you have only one Gibbs measure. So here you have only uniqueness. You have an existence because I just told you that you can define the Gibbs measure using accumulation point. So you have at least one. But this is kind of impressive because it doesn't matter how crazy your model. If you have very high temperature, only one measure. This is totally general, doesn't depend on the model. You have to impose some regularity on the interaction, but it's very general. Basically, all the models satisfy this. So in high temperatures, uniqueness. Okay. So now you see, if you assume that you know a priori the Dobruch uniqueness theorem, it makes sense this definition, because it's telling you that if you are at low temperature, at some moment maybe pop up a new Gibbs measure. So that's why this is kind of intuitive in definition, because you see, maybe you have to increase the beta. You have to increase certainly, because if in high temperature you have only one. So when beta is very large, means temperature is low. If it appears more another measure, so you have a transition. Okay, so now is the thing. This is a very old model. I can write again the Hamiltonian. It's just this. I will put this symbol to first neighbors. And okay, if you put, I don't know, maybe plus boundary condition, so you put this or another one. Here in the box, and actually is the phone in the box, and this guy actually I think maybe the best way is just say that you are here, and okay, let's say that the distance between the boundary is 1. Okay, is this guy, and you, of course, if you this is totally general, so you have this guy here. Maybe, okay, maybe put the entire, but I feel very bad to write something that is equal 1 in any case. And okay, and the distance should be 1. So if plus, you are just put just a minus plus here. This is the Hamiltonian, and there is no field, nothing. And okay, this is the most famous model. A lot of literature about this, and as I told you, the in high temperature you have only one measure that we just learned, and if you are in low temperature you have more than one, and to be precisely you construct these different measures assuming plus and minus boundary condition. Well, and this point where you change the set is precisely the point where the pressure is not analytic. So this is that's why one of the reasons that people assume one definition or another one is precisely because this model essentially. And to be honest, after we were discussing this, and at some moment I realized that I didn't know a proof of when the pressure is not analytic for dimension bigger or equal 3, and I wrote to some people which are specialists, and they also don't know. And it's just probably they should be exist, but I don't know. And in the dimension 2, we know because we have a closed formula for the pressure. So we know precisely who is the pressure, so we can identify the point where the function is not analytic. Okay. And now we start the more or less our history here. There is a term very general, and which the paper of Li and Yang is difficult if you are a mathematician, but Huel wrote another proof which you can read. And the important thing here is what I'm saying. This term is saying that if you put an H which is positive, which means that you have your Hamiltonian. Let's keep for the moment first neighbors, and you add a field, which is the same for. Let's put X. Doesn't matter how small, could be very large also, but different from 0. So you immediately destroy any chance of phase transition. So put an external field which is uniform, no phase transition. Extremely very old result. Everybody knows this. Physicists, mathematicians. If you are a mathematical physicist or you are a physicist that work in physical mechanics, everybody knows this here. You use you can prove using convex analysis or complex analysis also. There are different proofs now. But surprisingly, there is also literature about the random field, which when you put some distribution of these variables, which is a famous case also. But I was a student, and as I said, in Brazil there is no strong school in mathematical physics, and we were discussing with my colleagues, and about what happens if we consider, let's say, take a field which is decaying to 0 at infinity, for example. Of course, a lot of calculation that you do when the field is uniform, you cannot do anymore, because somehow you have some kind of translation invariance property if the parameters are uniform. But if you add something like this, you don't. Some calculations start to be a little bit more difficult. But we didn't find anything. So I was passing time here in Normandy with Robert Fernandes in Rouen. And I asked him, he didn't know also, and he passed it to me all the literature that he had about this kind of question in easy models. And maybe I will skip this. No, this is just a definition of pressure, and I have to discuss the pressure very fast, because exactly this is the point. One important thing that we are here in ZD, and in ZD is a minimal group. A minimal means that when you take the infimum of the boundary of the finite sets of the volume, gives you 0. One collection of take the balls, for example. So ZD is amenable, and actually you can study the easy model in any graph. But if the graph is amenable, what happens that the pressure when you take any boundary condition does not depend of the boundary condition, is a well-defined function. Essentially, what kills the boundary condition is the amenability of the graph. Will appears for you this kind of ratio, and this will kill the boundary condition. So you can put any boundary condition in the pressure on a finite volume, you take the limit, the graph is amenable, the boundary condition disappears. Okay. And now we start the, let's say, the not so intuitive behavior of this class of models. So one thing that happens that take any field decaying to zero, doesn't matter the speed, the availability of the graph will kill the field. So which means the pressure of the any field decaying to zero, doesn't matter the speed, is equal the pressure of the model with zero field. And we know, if you remember, for example, that in dimension 2, for example, we know that the easy model in dimension 2 has a point where the pressure is not analytic. So all these models doesn't matter how the field have a point where the pressure is not analytic. All is essentially the point is the same, which is actually that is written here. So you see, so you have a class of models which you can perturb something which decay to zero at infinity, and which have they have the same pressure. A lot of models with the same pressure, and this pressure has a point when which is not analytic, the pressure there. And well, this is Leandro was my colleague in Brazil. We were PhD students, and this was the first. This is Journal of Statistical Physics, and this was the first paper in the literature about this kind of models. And I should say that nobody believed it in the beginning. People sometimes make jokes, because what happens is, if you will discuss with a physicist, will happen the following. You will say the following phrase for him: okay, I have the easy model and they have positive field in each seat, and the model presents phase transition. Immediately he will say that it's false, because the literature until then is some kind of all the fields were uniform. So it was too strong a statement say that you have a positive field and phase transition at the same time, because of Young theory, and also because they have some kind of intuition of the people were in some sense about the uniform fields. So okay, we wrote the proof, and okay, I came back to Brazil after time here in France, and okay, nobody believed it. So I wrote to Roberto, and Roberto said, okay, Rodrigo, it's very strange, but I don't find anything which contradicts this theory. So write to Arno Netter, which is a guy from Netherlands, a famous guy from statistical mechanics, and ask him what he thinks. And Arno said the same thing. Very strange, but it seems okay. Nothing. There is no contradiction in this theory. So at the end, okay, the proof is okay. The first proof was wrong, really, but after we fixed it, and this was the first paper which nobody believed. But the hypothesis here, it was too strong. We asked some ability of the field. So this is okay. After we discovered that with this kind of condition is too strong, even the critical temperature is the same if you put this. So you are going too fast, and we start to investigate some kind of sharp condition of the decay of the field. And okay, this is a technical condition, but let me explain the intuition behind. What happens in these models that you try to prove that when you have minus boundary condition, for example, since the system is ferromagnetic, you here zero, for example, you are forcing, giving more probability to align the spins with the sign of the boundary condition. And so you have minus outside should be a positive probability, or good probability to see minus here also. This is the way that you construct the different measures, plus and minus. But suppose that you put a positive field. So put field here in the positive direction. So there is a fight, you see, between boundary which is here. You have some kind of boundary and volume of the field. Here's the field. You see? So essentially, this inequality is okay. To do the proof, you use exactly precisely the isoperimetric inequality, which is the mathematical tool that you compare boundary and volume. So this is some kind of some kind of adaptation. Okay, to prove the phase transition. Okay, this is a condition that you put, but after you can relax something. But you essentially what is telling you that the boundary wins respect to the field. So which means that the boundary forces to align with the boundary, and then you have different measures and then phase transition. So this was a collaboration with people from L'Aquila, Márcio Cassandro and Enrico Bresutti. These are guys from this home school of physical mechanics, and we wrote this paper with them. And but here it was some kind of strange at this moment. Now you see, we discover some kind of critical exponent. You see, is precisely delta equal 1. So if the field goes, let's say, faster, is bigger than 1, so the field behaves, the model behaves as a zero field. So if the field decays slowly to 0, between 0 and 1, so you have a unique Gibbs measure for now. For the moment, at this point, we have only for the very low temperature, which was very strange. We tried a lot to fix this during the collaboration, but we didn't succeed. And which is something like that. We have uniqueness here by the operation that I told you. We have uniqueness here by our proof. But what happens in the middle? So we told to the people, and everybody was very upset about this. But actually the proofs were difficult, and we were able to glue this region, at least not with a direct proof. So okay, for low, very slow field, and then after in the next year, Leandro with his student, is Roberto Villa, they glue. Essentially, they use some kind of graphical representation, and you have some kind of monotonal quantities, which if you have a monotonal function which here is 0 and here is 0 também, so should be 0 in the middle, and they fix it. And okay, final conclusion is the following: you have a concrete example where the pressure should have a point where it is not analytic, but you have a Gibbs measure, a unique Gibbs measure for outer temperature. This is very concrete. Is some kind of now you have another models with not easing, but this was the first in this class of easings that you have a pressure is not related with the change of number of Gibbs measures. So okay, so I'm very slow with respect to why I plan it. So I will do the following. I will just say a few things about the dimension 1, and just comments about the literature, and go to the multidimension and then the talk. I have 1 hour more or less. They told me, so let's more 10 minutes, let's say. And okay, so this was basically my main background, let's say, because it was we discovered this. There was a gap in the literature about because people know a lot of they know a lot about the random fields and a lot about uniform fields, but the literature about deterministic. Also, they consider periodic sometimes. But this idea of get something go to 0, it was new at this moment. And okay, so now to go to the everything that I said until now is bigger or equal to. And now there is this very famous paper of Froelich and Spencer, and that they solved an open problem which was open for a while. Now the dimension is 1. You have the dimension is 1, and the interaction is precisely what I told you. But the situation is the following. For alpha, you have to assume alpha bigger than 1 to not explode the energy function. So is 1 is open, and after 2, it was more or less the proof is not difficult to prove that let's say the interaction is too weak, so you have only one measure. So here you have uniqueness. People and for this reason, there is this hierarchical model that Dyson proved, and here you have phase transition. And so at this moment there is this open problem that what happens in this alpha equal 2, and this was solved in this paper. And this paper became very famous doing many things, but one thing that they have a new definition of contour, which means that you have, when you do this kind of proofs, you work with bubbles. Let's say you have a contour and you have some kind of minus outside, and plus you put plus inside, and this more or less is the way that you construct what the people call contours of piles. But this because it's short range. So if you have long range, it's not obvious what are the objects to consider. I mean, there is a strong gap between short range models and long range models. This is I mean, it's really challenging to do. And even so, because you see this picture is bidimensional. You see what is a contour in the one dimension. You can make take intervals, but does not work. So what works really is consider groups of intervals, which are they respect some kind of rules of distance. Let's say intervals which are close. Intervals which are close enough, you consider as a contour. If you are close, so this will be a new contour, and if you have a group another but far, this will be another contour. So it was really new idea at this point, and they proved they closed the gap of the interaction. And this became a lot of people wrote papers based on this, and we did some contributions on this class of one-dimensional models also. But after a while, we tried to jump to the long-range systems, which are these that I mentioned to you in the beginning. So exactly the same structure, the Hamiltonian. You have a field here that after you have to decide what is the decay, and you put this to be finite energy. And this was let's say, our last main result on the theory. Basically because, I can tell you after in the end of the talk. Basically, we had to read out at least good amount of part of these papers to produce the proof. And for those that if you are interested in to know what is a contour for a long range system, I have on my homepage a talk only to construct the contours. So is a talking Helsinki seminar, and they have records of the talks. They have the link in my homepage. So the entire talk is to construct what is the objects for this type of models. And okay, we base on this. Okay, maybe this is a sketch of the proof why we have the proof. And okay, so maybe it's just a comment that I'm writing in the end. What happens is the following: in dimension 2, when you have a contour, which essentially is some kind of closed, non-overlapping curve. Of course, everything is discrete here, and you have the leg. But why you're considering this? You are considering this because the interaction is short range. Essentially, you when you construct a contour, essentially is to separate different signs. So what you see here is exactly this. Okay, what you do, so what appears in the calculation is some kind of this, when this is the let's say the boundary of the contour, this kind of quantity. But when the system is long range, you don't have just the interaction between the neighbors. So what happens that if you have a plus here, these plus guys, they will interact with every single side of the lattice. We interact with everybody. So the key quantity here is exactly this. You have to estimate the interaction between a finite region from outside with inside with outside. So this is the key quantity for this model. So what happens that we know more or less the behavior of this quantity, and at least for balls, you see. So I'm more or less I'm telling you more or less what's our strategy to guess the exponents. One important thing in this kind of problem, you don't know the right exponent a priori. So in general, you start with very simple models. This is a heuristic with using balls, just balls. But the configuration could be extremely more complicated than this. But what you do very simple things, and you start to create some kind of intuition what should be the right answer. And okay, it's what we did. This is kind of a heuristic argument, and using this quantity, and this quantity for balls, you know precisely what is the behavior of these quantities. And you see here is more or less what you will find in the physics literature. In the books, not exactly mathematical physics, but in the physics literature, they know more or less already that if you are bigger than d+1, the behavior of your model, the model behaves as the short range. So you are decaying too fast, you see. And this, if you open a book about the long range system, they know this. So this is the let's say the new thing will be this part. Actually, again, people didn't believe in the beginning, but now we have a proof. And also you can if you consider fields like this, you can bound this the volume of field. So the more or less now, if you what happens that we control everything. We control the interaction between inside, outside, and the field. So we can go back here, and this essentially is the proof, the idea of the proof for this toy model. And this quantity should be positive. So you just compare the exponents and you guess what you should try to prove. This is more or less the strategy of someone working in statistical mechanics So in general, you do some kind of simplifications, and after you are increasing the complexity until the real model, let's say. So we have to guarantee that this is positive, and this you just compare the exponents of these functions, these quantities here. And the final answer is this graph. So now what I told you, you see, here is one, and here this point precisely is the corresponds to d plus 1. So more or less, people know that if the field, here is the field, the exponent of the field. If the field is strong, should be uniqueness, as you guess after Liang theorem. So here it's not really, nobody is surprised with this part. But this is strong. This is very new. This part here. So the main, and here I'm talking about the alpha between d plus 1. This is the new part of the result. Before us, Hueli already proved it, actually. Hueli and Ginibri, they knew it, that they have uniqueness for this field. The field is strong enough, and over the line you have to put some kind of parameter to find the phase relation. We don't know the proof of the uniqueness, and this is the archive we put in the last year. We are very confident that will be published a very good journal, because we also had to invent some kind of new contour to do the proof. So exactly this, as I told you, this okay, these papers of Fröhlich and Spemper, they are famous. Okay, first because they have an extremely new idea for this time. Actually, this solve this problem for animation, but they used the ideas from the previous one. And okay, but basically we had to combine all these papers with some kind of some adjustments. We're using some kind of a little bit of the Park also, and to discover what is the right definition of contour for these models. And this was I mean, the more let's say, you have to guess what are the geometrical objects to the model. This is the difficult part. After you have some kind of usual path to get the different measures. So you see, they have here is a kind of 88, right? But what happens that they can treat pods also, but even worse than Hueli. You see, is a new paper, but the result is even worse than Hueli paper, which is much older, as you see, 66. So here they already have D plus 1, but only for easing. So this guy Park is I mean, the Park use ideas, some kind of ideas of road expansion. They can also consider Potts model, but the respect to the exponent is worse. And okay, and the next result is us. So that's why we are waiting until the answer, but certainly will appear in some very nice place. And okay, I more or less I use all my time. I just let's say mention to finish that this motivate us to try to find other phase relation which is not really related with the pressure function, even in Edgar theory. So we succeeded to do this in the quantum Markov shift. We have phase relations with respect to the volume of the measure. We find this in the these are also Sarigi. Oh, okay, entendi. Something happening here. Okay, come back. We also have this behavior that the pressure detects some kind of resistance of eigenmeasures in quantum Markov shifts. This is a point where the pressure is not linear and beta, again in quantum Markov shifts. So you see, you have some kind of result which is strongly inspired by statistical mechanics in thermodynamic formalism. But okay, we find something that okay, it was published in this. This is my former two students. Elmer is Peruvian, and Eric now is working in New York University, Shanghai. And okay, it's a phase transition with respect to the volume of the measure, but again, the pressure does not see this change. And we have also for the generalizer, but I think I will stop here. It's 1 hour already. So thank you. I can answer questions, or I can say anything.
Okay, thank you very much. So I was asked by Gniewko to chair discussion part. So if you have any questions or comments. Okay, so let me ask myself a question. Okay, so you discuss the behavior of pressure. Do you know a critical exponent as a critical temperature for pressure when you face phase transition?
Well, is like that. In these models, okay, you say that suppose that I have a field which decays to zero fast enough to see the phase transition.
Yes.
If you know the critical temperature, no. And okay, let's say there is an abstract theorem of you can find in Georg's book, which says this, if the field is summable, so the critical temperature is the same. So the model is not the transition invariant anymore; it's different model, but the critical temperature is exactly the same. I think Sokol also proved for the Potsdam. It's actually a general theorem from Georg's book. So if the summable, the same. If not summable, probably you just you just move a little bit, but I don't believe that it should be possible to calculate the critical temperature. To be honest, I guess there's a conjecture. Maybe on Michael Eisman homepage you can find something that people are speculating that maybe we never will find the critical temperature of the Ising dimensional tree. So we know we know the value for dimensional 2, but dimensional 3 we don't know.
Okay, but do you know any numerical results about that?
No, unfortunately, to be honest, I was in some kind of conference time ago and tried to find someone to do simulation with this decay of fields, and nobody was interested. I don't know if it's difficult or maybe people don't like, but I don't have simulations with decay of fields. I don't have, but maybe it could be a thing to do. Yes, is the following. Probably the temperature is not the same. I don't have a proof, but I don't have even any guess. Let's say how far is from the original one. I don't have it. Neither this.
Okay, I see. Thank you. Are there any questions? Yes, Wodek, please.
I wanted to ask what Darek has just asked about the computational simulation, because there are so many papers where these simulations are done, including some of these quantum annealing computers that could probably be used for such simulations. But also I wanted to know if you see a chance to connect what you're doing to some kind of a model experiments that people sometimes do on the systems that resemble, let's say, I mean, connection with the real world, so to say.
Well, this is a very funny history. You know, now with Google Scholar, you can follow who are the people which are citing you, right? And this maybe is a bit is a bit sad because in general they see the first one, which is the weaker, but since is easier to read, maybe because of this. But people, I think the financial market, something in this modelizing something in financial, they sit in my paper. So I don't know the result, but because okay, to be honest, it should be the following: the easing model they use in a lot of real things. I mean, they put the easing model to yes and no, and the field should be something to give more probability to no or to yes, depending of the sign. But I didn't follow what they prove it really. It seems not so let's say deep result. They just find our modification as something that is not uniform, and they just did. They use it, but I don't know really. I think it's not really. I mean, very relevant, I guess.
Okay.
Okay, thank you. Other questions or comments? But what about other quantities? Because you discuss only pressure, but you know very often people discuss
the case of correlations, for example.
Correlations or for example specific heat, right? Specific heat and critical exponents for a specific heat.
Now we did. I think the case of correlations at some moment we tried, but the problem that to do the calculations with this, the field is not uniform. A lot of things that you do with the, I mean, during the proofs you use strongly the fact that you have some kind of uniform parameter. So the calculations became very difficult, and we didn't find anything. Maybe we can prove something that let's say analogous because you know there is some kind of paper of Fernandes, maybe Eisman, Barsky, Fernandes. They proved that exactly the critical point you can characterize for a big class of models of Ising type models included. They proved that the case of correlations also characterize the critical points. So maybe you can guess that the correlations decay fast enough after the critical point, and so on, also for these models. But we didn't have any result in this direction.
I see. Okay. Any further question? So let me ask also about periodic boundary condition. I mean, if you replace just ZD by D-dimensional torus.
Okay. Okay, so the periodic boundary condition is inside. Okay, one thing that you can prove is that the extremal points are the same, which means that you find the extremal points of your set of Gibbs measure also with the plus and minus boundary condition. So if you put periodic boundary condition, you just will get another Gibbs measure, which in this convex. I mean, is an interval in dimension 2, right? Because it's dimension 3 or more, you have this Dobrushin boundary condition. It could be very complicated, but in dimension 2, I mean, because okay, the truth is, even dimension 3 or more, we don't know precisely what are precisely the extremal Gibbs measures for Ising first neighbors. We don't know. People believe that it is the only plus and minus and Dobrushin boundary condition, but there is no proof. And so if you consider a periodic boundary condition, so you will get a Gibbs measure, which if you are in dimension 2, with some kind of point of the interval between plus and minus, in just this.
Okay, I see. Okay, so this is the last chance to ask a question.
Just a comment that Actually, in the beginning, I was planning to talk about the quantum things also, but after
Yes, this is my question. Yes, this is my last question.
Yes, actually, our let's say our recent results, but is okay. Okay, let's okay. The thing. One of my main projects now is put boundary conditions in the quantum models, because there is no boundary condition quantum models. People do with free boundary condition for any model. This is totally. Yes. This is very bad because you don't have tools to prove phase transition. The proofs are very artificial. Let's say using Zor lemma, things like that. I mean, it became a problem because you don't have boundary conditions on the theory. There was some tentatives in the past, but they failed. I know that Pierre Picot in Marseille, he put in one-dimensional long-range kind of quantum easing, but he never put the preprint in the archive, so I don't know if he finished or not. But we are very advanced in what we believe that is very promising proposed. So I guess in the next year maximum we will have a theory of quantum, at least for spin models, let's say. Quantum spin systems, I'm very confident that we will put boundary conditions there. So we believe that will be this finally will be a big impact in the theory, because with boundary conditions you can construct more KMS states, right? So this will be our hope. So we don't have for the moment, because you see, all my approach is based on boundary conditions, and in the quantum side, until now, but soon we will have, there is no boundary condition for the moment. Even I discussed with a guy of Fermat systems, and he believed that all the KMS states came from the free boundary conditions. This is, for us, from the classical side, is totally not true, because for us we use strongly the boundary conditions to construct the Gibbs magic.
Right,
so
right.
You see.
I
so
see. Okay.
So wait 1 year.
Okay.
Wait 1 year. Okay, maybe 8 months. I don't know, but we are very confident, because, to be honest, it's the following: we have read the object, but we don't have examples. So we are getting the, let's say, the easy quantum easy with external field, some transversal field, and we are doing with this kind of model, and it seems that will work. so 8 months.
Okay, very, very nice. So I do not see any further questions. So let me thank once again for your very interesting talk. And I close the seminar.
Okay.
Thank you very much.
Bye-bye.
Can we